is an introductory course on circuits and systems or networks and systems suitable for an undergraduate student majoring in electrical engineering with either the power or communication option. In this course, we will study the dynamic behavior of systems and networks. You will be exposed to a variety of tools and techniques which are used to study the behavior of these systems with the dynamic inputs, so that you can gain an appreciation of what particular techniques to choose under a given situation. When talking about systems, we should also talk about signals. The input variables to a system, the response variables that we are looking for, and the various intermediate variables which occur at different points in the system are all collectively called signals, and this is a term which we will use to describe these variables associated with any system. Later on we will say that a network is a special kind of system, and the voltage and current variables associated with a circuit or a network therefore are also called signals in the particular context of an electrical network. These signals are usually functions of time. A study of the characteristics of these signals and their analysis therefore is an integral component of our course. As a matter of fact, it is the interplay between the signals and systems that will be the main theme and focus of our course. Among the topics which we will study are Fourier methods, Fourier transform, Laplace transform method, network functions, network theorems, Z transform methods, and state variable techniques. These will be the various topics that will be broadly covered under this course. We shall, for the most part, confine ourselves largely to the discussion of linear time invariant systems. The meaning of these two adjectives, linear and time invariant, will become clear as we go along. Suffice it to say that they form a fairly large class of useful systems. So at the end of this course, you will have with you a toolkit of available techniques so that you can choose one of these techniques for the solution of the dynamic behavior of a network and system belonging to this very large class of linear time invariant systems. Before we proceed further to discuss the meaning of a system, let me first talk about the various textbooks and reference books that you may like to refer to during your study of the material under this course. You may use these books to have some of your doubts clarified, to deepen your understanding of a particular topic, maybe to get additional information related to some of the topics that are discussed here. But most importantly, you should use these books for working out the various problems and answering the various questions that are given as exercises in these books. Particularly for a subject with an analytic orientation like networks and systems, it is very important that you should work out a large number of these quantitative problems and answer these various questions. It is only through such exercises that you can form your understanding of the subject, make your grip of the various techniques stronger. And another important aspect with this is that, like in any other discipline, in networks and systems also, there will be always a number of approaches to solve a particular problem. Only through working out these various exercises you will be having the ability to choose the most direct method of attack for a given problem. You will have the necessary expertise to gain the insight so that you can select the most appropriate method of attack for the solution of a problem, and not only that, to carry out the solution correctly and in quick time. So I would once again emphasize the importance of working out a variety of problems, and you can use some of the textbooks which I am going to mention right now as a source material for these problems. Now, the particular textbooks that I would like to recommend are Haight and Kemmerly, Engineering Circuit Analysis, Van Valkenburg, Network Analysis. These two are very popular books in this field. Oppenheim, Wilsky and Young, Signals and Systems is very comprehensive. It gives a very comprehensive coverage of the topics that are covered in this course, plus some additional topics. And this also contains a wealth of problems as exercises. In addition to these three books, you have a book by Cheng titled Analysis of Linear Systems, Liu and Liu, Linear System Analysis, and a sixth book by Athre, Network Theory and Filter Design. It contains discussion of some of the topics that we are going to cover in this course, like state variable methods and so on, which are not perhaps found in some of the other books. By way of background, I expect of you to follow this course. Let me mention that I expect the students to have a background on the following topics. I would assume that you have had a basic course in electrical circuit analysis, which includes the discussion of the properties of various circuit elements, DC and AC circuit analysis, AC circuit analysis under steady state sinusoidal conditions, and an idea of elementary transients, the time constants in RC circuit, RL circuit, and so on, and setting up the differential equations pertaining to simple circuits. This is a background in electrical engineering that one would assume. As far as mathematics is concerned, you should be familiar with elements of differential and integral calculus, solution of simple linear differential equations, ordinary differential equations with constant coefficients. You should also have an idea of matrices and determinants, solution of linear algebraic equations, and then elements of complex variable theory is also expected of you to follow this course. So this is the background what one would expect you to have to follow this course. Now let us discuss what a system means. All of us intuitively have an idea of what a system is constituted of through its usage in everyday terminology. We may formally say a system is a collection of components put together to serve a particular purpose. These components are system components, as they are called, are unified through some kind of interdependence among them. They react with each other so that the whole system functions as a whole to serve a particular purpose. We may think of a power system, the national educational system, hospital systems, railway systems, transportation systems, and so on and so forth. Many of these systems also have as an integral component the interaction of people, for example, in socio-economic systems. All these are constituents of systems. Now, therefore, a system is a collection of objects united through some form of interdependence among the various components, or subsystems, as you may call. Now, the variables that describe the status of these various components in a system may be quite diverse depending upon the nature of the component, the nature of the system, and so on and so forth. For example, if you are talking about an electromechanical system, you may have the electrical variables, voltage and currents associated with the electrical components, and mechanical variables like force and velocity, which describe the status of a mechanical component at a particular point in the system, at a particular point in the system. Therefore, system is an omnibus type of concept which includes a whole variety of situations that one comes across. Now, what about a network? Literally speaking, a network is a structure which resembles a kind of net, but in our particular context we use a network, the term network, to describe a system in which all the components are of a related kind. That means the variables which are of importance in the system are all of the same kind. So, in a particular electrical network, for example, is a special kind of a system in which the variables are voltage and currents most often. That is, these are the two variables which are of interest to us in an electrical network. Similarly, we can have a network representing a mechanical system, which we will call a mechanical network, in which the variables may be velocities and then forces and so on and so forth. So, we can think of a network as a special kind of a system. An electrical network in particular is what constitutes the focus of our discussion here. Now, in analyzing these systems and networks, the first step usually is to model the system in terms of idealized components put together in a particular fashion. This evolution of the model is done with the two conflicting requirements in our mind. What are the two conflicting requirements? First of all, we should like to have the model as realistic as possible so that it simulates the real system. In other words, we should like to make the model as complex as possible so that we lose as little information about the system as possible. On the other hand, we should also like to make the model as simple as possible to lend itself to convenient mathematical analysis, so that the person who uses this model for analysis and synthesis will retain his sanity in a sense, because if it is going to be a huge a complex type of model, he will never be able to solve it. Therefore, these are the two conflicting requirements in the evolution of a model of a given physical system. On one hand, it should be as complex as possible so that it will lose as little information about the system as possible. At the same time, it has got to be simple enough to lend itself to convenient mathematical analysis. Now, we very often refer to the model itself as a system, even though we must always keep at the back of our mind that the model is a mathematical representation, is an idealized representation. The actual physical system is something different, and in some ways the physical system may not, the characteristics may not agree with the model, and if it is so, then we have to refine the model to make it more realistic wherever it is warranted. Now, in arriving at a model for a particular system, the derivation of the model is specific to the particular discipline. You must study the physics of the situation, you must know the characteristics of this and arrive at a suitable model. But once we have evolved a model, then a whole lot of the systems can be analyzed through a common framework, a common set of mathematical tools which can be used to analyze a whole lot of these different system models, because the mathematical equations that govern the operation of these various systems are more or less the same. Therefore, there is a unifying body of techniques and knowledge which come under the general title system theory or principles of system analysis, which will be the main scope of our study under this course.